All right. So we are going to do a little bit now on the fundamentals of optics and image processing. Again, my name is Shaptarshi Basu. These lecture notes are once again courtesy of Professor Cameron Tropia, who is my long-term collaborator. And this is also a part of the lecture that he delivered at IISc during a short course here. All right. Majority of the materials are taken from him with a little bit of interjection from other places as well. So if you look at visualization in general, this is, for example, a droplet which is impinging on a mask or a porous substrate. This is a vortex which is interacting with a liquid-infused porous media. Here you can see it is a vortex which is interacting with a tear film. And lastly, you can see that this is a shock wave droplet interaction. So in all these things, you can see one thing is common, that we are using optics, and techniques like Schillerine, in some cases some cases like particle image velocimetry. In some cases, it could be also LDV and other kinds of things to basically visualize the flow field or visualize the events, be it the flow field, be it the structures, etc., etc. So this therefore requires, as the subject of this talk actually suggests, we need to know the fundamentals of optics and image processing, because this is what has come out after very careful optical arrangements and after very careful and rigorous image processing. So you need to know both in order to to get an idea that what we are doing over here. All right. So this is of paramount importance if you want to get quality like this. These are all from my research work, or the research work from my group, as you can see. And these are varied events, very high speed. This is, for example, very high speed because there is a shock wave. On the other hand, this is, for example, more or less low speed event. Okay. This is also medium speed. Okay. This is also medium speed. So you can see that you can image different types of events, very high speed to very low speed as well, if you got your optics and imaging correct. So that is the whole point over here. So the contents of this particular lecture will follow what Professor Tropia did, that there are some optical fundamentals, and then there are some visualization stuff like hardware. Then, of course, how light propagates and scatters. These are of vital importance for many measurements that are going to follow after this. For example, light is an electromagnetic wave. It has coherence. It can be polarized. Then, of course, Snell's law, which you might have seen earlier in your high school and undergraduate physics. Then Fresnel equations, the Lorentz-Mean theory, the geometric optics, and scattering from small particles. Okay, all of these are very crucial when you actually go on to study the more detailed diagnostic techniques. And then, of course, there are image processing fundamentals. So these are all optics. There are image processing fundamentals. So image processing fundamentals is also very important, because once the images that you get, how do you process it to recover information which sometimes may be embedded inside it? All right. So that is the whole point of stating that what are the image processing fundamentals. Okay, this we will also have videos which will showcase that how the images are actually processed. Now let's look at imaging fundamentals 1, which is basically if you have waves which are basically a point source, and you have this light waves which are coming out as spherical wave fronts. Okay. So as they interact with a spherical interface, so this is a spherical interface, you can actually have plane waves propagating through it. All right. You can also reshape plane waves. In this case, this is a plane wave. Say what is coming out of this may be plane waves. Okay, highly collimated beams. Now you can use a spherical interface, is this, and you can focus the planes into spherical plane waves into spherical waves, and you can focus it right at this particular point. So this is basically what lenses do. Okay, And this is also what lenses do. They make collimated beams as well. So plane waves propagating beyond a spherical interface. This is what you see. This is plane waves which is coming and interacting with a spherical interface, gets converted into spherical waves, and it gets focused at the imaging, at the image focus. So all these things, this is the lens, which is, you are very well conversant with what lenses are capable of doing. So this you know from your high school physics, most likely. This is not rocket science. Okay, so imaging fundamentals 2. So if you have a thin lens over here, so let's assume this is a thin lens. So there is an object which is given by that, which has a height, which is y naught. Now this object, this is the imaging plane. So you form an image of the object, in this case an inverted image. So what happens is that this is the lens, which basically forms that image. So the image has a dimension of yi. Now the thin lens formula is known to most of you, which is basically 1 by s naught, which s naught is the distance of the object from the lens, then 1 by si, which is the distance of the image plane from the lens. The inverse of summation of the inverse of these two quantities is equal to 1 over the focal length of the lens, which is the focal length right here that you can see. Okay, so this is the focal length of the lens. Okay, now, so this is the thin lens formula. This is very common, you know this. Okay, now if we look at that, there can be two magnifications possible. What is a transverse magnification and one is a longitudinal magnification. So the transverse magnification is rather easy. It is basically given as yi divided by y naught. So basically the dimension or the vertical height of the imaged object to the actual object. And that is given as a ratio, because if you just follow the ratio, it is given as si over s naught. Okay, so si over s naught. All right. That is given as minus xi over f is equal to minus f by x naught, where x naught is this, okay, xi, as you can see, is this, right? So the f being the focal length, right? So this is the transverse magnification that you have, all right? So this is how much it is removed from the focal point, right? How much it is removed from the focal point. So the longitudinal magnification, on the other hand, is given as dxi by dx naught. Okay, in this particular direction, in the horizontal direction, and that is given as minus f square by x naught square, right? So the transverse magnification and the longitudinal magnifications are given in this particular form, right? So based on this, so this is this comes from the thin lens formula, and this very basic arrangement you already know, I suppose. Then imaging fundamentals 3, so you can see that you have an object and you have an image. Now, if you have, for example, there is a light bulb here, okay, and you know this passes through this focal point. So what this lens actually does is that some of these beams are actually diverted in this particular fashion, and you form an inverted image of this light bulb. That is what you get to see over here. This is a convex lens. And you can also have, a concave lens over here. And there, of course, you form the image on the same side, not on the other side, same side, and it's not inverted. It is not an inverted image, but this is the image that you actually see over here. Okay. So what you can see, a real object and a positive lens, and a real object and a negative lens. These are the two examples that are shown over here. Now, here are some of the quantities, S naught, real object, and then your virtual object. All these signs you can actually can put it in the form of a table. So whether the image will be erect image or inverted image, that is what you can actually see over here. Okay. So in this case, for example, this is an inverted image. All right. You can just do basic ray optics, basically to trace the beams, and you can get an idea that how the image will actually form and what will be the magnification of these images. Okay, here you can see clearly it is magnified beyond 1. Here it is magnified below 1. Okay, So it is actually diminished image, so to say. Okay, so these are things I think it is well covered in your undergraduate or in your other types of things as well. Okay, so the images of real objects are formed by thin lenses, right? So when the location, object location, is between infinity to so infinity, so the S naught, I just go back over here, this is S naught, the location of the object from the lens, if that is the case. Okay, so if it is if S naught is greater than 2f, okay, but less than infinity, okay, you get, and if you use a convex lens, you get the real type image. The location of the image is located between the two focal lengths, that is SI. You look at it, this is SI, this is the location, and it is inverted and the size is minified. Now, if S naught is exactly equal to 2f, the location of the image is also at 2f, and it is inverted and is of the same size, right? On the other hand, if the object is located within f and 2f, it is real. The image is formed somewhere beyond 2f, and it is inverted and it is magnified. All right. And similarly, if S naught is less than f, then the type is virtual, and you get an erect image and you get a magnified image. Similar things happens for your concave lens as well, and there are certain rules that you have learned in your high school probably, but this is a table which tells you. So when you look at this table, please consult this particular figure, which will tell you that what are where the object is placed, and based on that, where the image will be, whether it will be magnified or minified, whether it will be inverted or erect. These are the decisions that you can get. Okay, so when two lenses are separated by a distance which is smaller than the sum of their focal lengths, as you can see over here, so this is the image that is formed. There's a rather complicated formula that you have, because you have two focal lengths now, f1 and f2, and you have two S naught as well, okay, S naught 1 and S naught 1, and then you have like SI1 and SI2 as well. So you can see that these two thin lenses are separated, but the distance of separation between these two lenses, which is d, okay, it is smaller than the sum of their two focal lengths. Okay, so it is less than f1 plus f2. So in these kind of cases, if you read this particular book also, is Jackass, so you can see that the total magnification in the transverse direction would be the multiplicative product of the magnification of the individual lenses. So these are only for two thin lenses separated by a distance smaller than the sum of their focal lengths. Okay. Now, if two thin lenses, are separated by a distance which is greater than the sum of their focal lengths, so the distance between these two lenses, which are very different focal lengths, for example, they are separated by a distance which is greater than the sum of their focal lengths, which is again d. Okay, so in that particular case, the effective focal length is given as 1 over f as 1 over f1 plus 1 over f2 plus da 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 1 over fn, the number of lenses that you can stack up. Okay, and when d actually starts to become smaller and smaller. All right. Now we come to the concept of aperture. So the aperture basically, so these are images that you can see. So the aperture refers to the opening through which the light passes before hitting our camera sensor. Okay, so it's basically refers to the opening that you have. This is the opening, this is the opening, this is an opening, this white center that you see. So f number, which is shown as f divided by this hash sign, is pronounced as f number. Setting on a lens controls the overall light throughput. That means how much light actually gets in, and the depth of the field, and the ability to produce a contrast at a given resolution. So these are three important points: that overall light throughput, the depth of field, and the ability to produce a contrast at a given resolution. So fundamentally, f number, okay, or f divided by hash, is the ratio of the focal length of the lens to the effective aperture diameter, which is phi EA. So f number is nothing but f by phi EA, which is the effective aperture diameter. For example, this is a large aperture. Okay, so effectively it is a small, f-stop number. So as you go on decreasing the phi EA size, okay, you get to lower and lower aperture. So this is, for example, a very small aperture, which is given as f by 32. Okay, so you are going on reducing, the diameter, the effective aperture diameter, and therefore you are increasing, or you are rather, your f number is actually becomes f by 32, for example. Okay, so aperture in essence refers to the opening through which the light passes before it hits the camera. This is the most important part. Then fundamentally, this also controls, which is given as an f number. It is a lens control parameter which shows the light throughput, depth of field, and the ability to produce a contrast at a given resolution. All right. So if you look at now these images, for example, here's a lady with a cat, and there is a tree. They are all at different depths of field. Okay, they are not in the same plane, so to say. Okay. So when you are doing a large aperture, this is a large aperture, okay, you have a very shallow depth of field. That means if you are focusing on this woman, she will be in sharp focus, not necessarily the background. Now, as you go on doing the light control, that is less and less amount of light is getting in, and as you go on decreasing the aperture, okay, which is basically you go from a large aperture now to a very small aperture, which is f by 32 over here. What you see is that you have a great depth of field. Okay, so you can see the the woman, the tree, and the cat. Okay, so large aperture means more light, and as you go on decreasing the aperture size, okay, you get less and less and less amount of light. Okay, so great depth of field comes with small aperture. Shallow depth of field comes with large aperture. So this is to be recorded, because in some cases you may need to image something with a very shallow depth of field. So you don't want light from you don't want other objects to be in focus, particularly important, for example, in micro particle image velocimetry. In that case, you do a shallow depth of field. Therefore, you need a very large aperture. Okay, but when you are going to a large depth of field or a great depth of field, you can deal with a very small aperture. Okay, so you understood what aperture is, what f number is, and how large and small aperture are related to the depth of field of the image. Okay, it is also convenient to represent the overall light throughput as a cone angle, as you can see. So this is kind of the aperture. This is the cone angle. As a cone angle, this is also called the numerical aperture of a lens. The numerical aperture of a lens is defined as the sine of the angle made by the marginal ray and the optical axis in the image plane. So this black line is the optical axis. This red line is a marginal ray. So it is defined as a sine of the angle between these two. Okay, sine of this angle, which is theta. So the f number and the numerical aperture are inversely related. That means numerical aperture is 1 over 2 of the f number. All right. So 2 by f number, 1 by 2 f number is actually the numerical aperture. So what is it once again? It is basically convenient to represent the overall light throughput as a cone angle. Okay. And the numerical aperture, so this is called the numerical aperture. It is defined as a sine of the angle. This is the angle sine of this angle made by the marginal ray and the optical axis in the image space, right? So they are inversely related. So f number, your numerical aperture, you can find out. So this is another way. They are basically one and the same thing. So this is kind of one convenient way of representing the same. Okay. Now the depth of field, this is taken from Ron Adrian's annual review of fluid mechanics. Okay. So the depth of field, as you can understand, is the distance between the nearest and the furthest objects that appear acceptably sharp in an image. So when you are imaging something, okay, say the image has a certain depth of field because objects are never in a single plane, so to say. So they have certain dimensions. So it is, for example, the droplet images that I showed when it interacts with a shock, or actually this particular video that I showed. Let's take a look at this, for example, one more time. So you can see that you can see the droplets, and you can see some of these droplets are very sharp, some of them are not. So the idea of that is that some objects which are within a certain distance, which is given as, say, DOF, which is dr plus df, around a certain focusing plane. So this is like the image plane according to which the lens assemblies actually work. But around that lens assembly, at a certain depth, inwards or outwards, okay, perpendicular to this object plane, you will have a reasonably or acceptably sharp image, as we showed in the case of those droplets. Some droplets which are within this band will appear as acceptably sharp. The droplets which are away will appear blurry. Okay, so the actual object plane is a single object plane which the lens works on, but there is a little bit of distance across which the image will appear moderately sharp. Okay, so this is quantified by what we call the circle of confusion. Okay, so this is basically nothing but a blurry disk that represents an out of focus source image. So source image, this is a blurry disk. This is called the circle of confusion. Okay, so the total depth of field is basically 2 times the numerical aperture multiplied by this C, which is basically the circle of confusion, multiplied by a function of the transverse magnification. The circle of confusion is approximately 0.25 mm, is universally used to specify the total depth of field. So the total depth of field is given by this particular equation. So to say where C is about 0.25 mm. So what is this circle of confusion? Once again, it is a blurry disk. You can see this is a blurry disk, okay, which represents an out of focus point source image, which is exactly what it is. Because these points, okay, are out of focus because they are not on the image plane directly. As a result of that, they represents an out of focus point source image on the imaging side of things. Okay, so this is what you can see very clearly over here. Okay, that where the rays actually converge. Okay, you can see that that is the circle of confusion. Okay, so this can also be represented, the DOF is given as dr plus df, and it can be approximated. This is an approximation. This is given as 4 into 1 plus 1 by mt square into the f number square into lambda. So this is the depth of field that is given. Okay, so you can understand why the circle of confusion happens, because the images are not exactly in focus, because the focal plane is a single plane over here. So these are around the focal plane, but so they form an out of focus image, and as a result of that, there is an extent of blurriness which should be acceptable to us. Okay, so this is what the image fundamentals actually dictates. Okay, so if you look at scenario, so you learned quite a few things up to this particular point in this presentation. You saw some of the very cool images, okay, which represents a lot of optics and a lot of image processing. You saw what a lens can actually do and what the kind of magnifications that it can do. And you also found out that, if you do this imaging properly, these are the different parameters, and based on that, the image is quantified. How they are quantified, what will be the magnification that we learned. But the two important parts were that we learned that when the two lenses are separated by a distance, and how their sum is the inverse summation of the focal length. But the most important concept that you learned probably here was the aperture, and how the aperture is related to something called a f number. The f number is nothing but f divided by the effective aperture diameter. So as you close in on the aperture diameter, okay, the f number actually becomes f by 32, for example. Okay, and in order to get a shallow depth of field, you need a large aperture. In order to get a large or a great depth of field, you require a small aperture. Light is more when you have a large aperture. because that is what it is, and light is less when you actually have a small aperture. Okay, and a numerical aperture is just the inverse of the f number, and it is given by the sine of the theta that the marginal ray makes with the optical axis. And now we also know one other stuff, which is basically the depth of field, and how the depth of field is given by the magnification number and the f number. And we also learned a concept which is called the circle of confusion, okay, which is a blurry disk that represents an out of focus point image. So these are some of the important concepts before we go on to something called diffraction. That is also very important, as we will learn later, but this kind of covers that what are the kind of normal imaging that you will come across in this particular course, right? So again, read through this very carefully and get your concept organized before we move on to what we call the diffraction.